told him to call him whenever there is a technical problem. So. Okay, now it's fixed, I think. Okay. All right. So let's continue. Yeah. So before, at each node, each particle could have only one state, right? If you occupy this state, then you are the particle going in this direction. If you occupy this state, then you are a particle going in this direction. Now, in this model here, in addition to their velocity, the particles can also be in different states. Okay, so you see, this is a red particle going in this direction. Here you have a blue particle going in this direction. Here you have a green particle. Okay, so you have much more information. So another way to see it would be that you add color to these arrows, and different colors can have different properties. Okay. So, all right. So what is the interpretation now? So you have much more states, and now the only difference. So the movement step is the same, right? So if you have a particle moving this way, it will move here in the next step, etc. The collision step now is not at all a collision step. The collision step becomes now an interaction step. So we interpret at all these points mean that the particles of different types are in the same location, so they can interact with each other. So before, we choose only the interactions that preserve momentum because we wanted to do a gas. Here, now the interpretation is that the particles are some kind of cells or some kind of creatures that interact. So you don't have any more conditions on the conservation of anything. You can do whatever you want. And so the idea is that now, instead of your thing simulating a gas, it simulates a population of some cells of different types, which have some predefined interaction when they arrive at the same point. So you see why it's called BOLGCA, because you can use it to model it like populations of cells, etc. And so the way it looks, just to summarize what I've already told you, this is one state of the model. Okay. At each node, you have particles which can be in several directions and with several states, which is the color here. Then you have the interaction step, which previously was the collision step. And here I just put random rules. Okay, for example, here there was a blue surrounded by 3 green. Let's say this kills the blue. Okay, so the blue disappeared here and then the green moved. Okay. Here, for example, there are 3 yellows, 1 which is stationary, the 2 which are moving. Well, this tells the yellow that it's gonna move. Okay, here you can choose any rule that you want. These are just random rules that I chose. And then the next step, which is the movement step or migration step, this one proceeds as before. So if you look, for example, this green here wanted to go to the left. So we'll plate it on the left hexagon and it preserves his speed. Okay, so it's still going to the left. And this yellow here wanted to go to this one, so it arrives here. This green wants it to go here, so it arrives here. This one is a stationary one, has 0 speed, so it remains here, and so on and so forth. And then you can do a lot of stuff with this. So one example, which unfortunately I don't have a video handy, was a project from a bachelor student, which used this LGCA, and the interpretation was that the cell in the middle determines the actual nature of the cell. Okay, so for example, this one would be a yellow cell because it has a yellow middle. And then the channels on the sides are some sort of pheromones or signals. Okay, so you have a cell which is green here and it will generate some signals that it will pass to the cell which are around them. And then according to the signals you receive, you will process them and then do something. And the goal in this model, I will add the video later or maybe at the break, was to create some cells that would kind of assemble and reproduce more or less just as DNA or RNA does. Okay, so you have 4 types of cells, A, C, G, T. They send signal to detect a cell which is compatible. When they detect it, they merge, and then they wait for a third cell to connect, etc., etc. And so they can form links and then also reproduce. Yeah, that's just an example. I just wanted to show the BLGCA because it's one which is used, can be useful. So the main difference, you might say, okay, why use the BLGCA and not just a traditional cellular automaton? The main difference here is that you have this notion of particle. Okay, in a cellular automaton, the movement is really annoying to do. If I want to move a white pixel from here to here, I have to kill the pixel here and generate it here. Whereas here, if you want to move the blue particle from here to here, I mean, it's baked in, right? It happens automatically. So that's the main advantage. All right, that's all for LGCA. Are there any questions on this? Okay, so let's proceed. So now the last system that I wanted to look is just one because it kind of makes a nice bridge to the next subject, which are continuous alive systems. Yes? Yeah. Yes.
I'm sure there's a lot of theory for this, but intuitively, why does this preserve the rotational symmetry when the square didn't?
Okay, so the question is why does the hexagonal preserve the rotation symmetry and the square does not? And I don't have a very precise answer for this, but the interpretation is that in both cases, you preserve a subset of the full rotation group at the microscopic level. And the idea that I have, at least, is that if you take a big enough subgroup, at the high level, you have no choice but to get the full rotational group. Okay? You somehow, because you are averaging over a lot of particles, how to say, yeah. Somehow you need a minimum amount of rotational symmetry at the microscopic level to force to have the full rotational symmetry at the microscopic level. Yes, maybe.
Yeah, I mean, maybe an example that I think would be correct is if you know you have a norm on R2, and you know that the vectors 1, 0 and vector 0, 1 have the same length. In itself, it's not necessarily a rotationally invariant norm, as for example, the L1 norm, the sum of the absolute coordinate, would satisfy this and not be rotationally invariant. Yeah. However, if you were to impose that three vectors that are rotations, I mean, three vertices out of the 6 of the hexagon are of the same length, I suspect that this would force the
to have
norm
the full
to be the L2 norm and as a result to be rotationally invariant.
Yeah. So it's some sort of like this, like when you have the subgroup at the microscopic level, it's enough to enforce like the full rotational group at the microscopic. But from the study they do, the actual study of how to recover the equations, it's not very clear to me precisely which point is where you get the full Laplacian and not. So in some sense, at the microscopic level, the diffusion process is just the Laplacian. Okay, so essentially you have these two derivatives, like dx and dy derivatives, and you have to combine them at the second level. And the idea is that if you have this 90 degree, you could still have the dx dy, which respects this 90 degree rotation. But it's harder to have a combination of these dx and dys that respects the 60, but not the full. Something like that, yeah.
So how many unknowns, how many equations?
Yeah, something like that, yeah. But
I guess because you have to respect, there's 3 equations.
Yeah,
right.
Instead of 2, so
yes, something like that.
So in theory, if you want to do the same thing for 3 dimensions, then hexagon would be enough.
Right. So the problem in 3 dimensions is that the only regular polygon that tiles the 3 dimensions is the cube. So you cannot do it with the hexagon. So actually, I looked. I didn't find how people do it. If they do it with, 2 polygons to tile the thing, but then it makes things much more complicated. So in 3D, I don't really know how.
But
in principle, I think yes. I think that is correct. Maybe more. Yeah, I'm not sure. I'm not sure what is the counting. Right? I mean, I'm not sure that dx dy is the 2 versus 3 of the hexagon, or it's.
Could be more than 4.
Yeah, I'm not sure. That's a good question. Okay, let me look at the second. Oh, God. Yeah, there are some comments here. It was the sound. Okay, that's fine. All right. So I want to move a bit more towards continuous systems. And this model here that I will present very briefly, it's kind of the bridge between the two. So that's why I wanted to present it, even though it's not particularly special. So in the GCA, we found one philosophy or one possible path to go from discrete to continuous. And this is to take a discrete model, but just consider bigger and bigger scale, coarse grain the small dynamics. So don't look precisely at what happens, just take the average. And then you get something which is continuous. So this is another approach to take a model and make it continuous. And it's to act at the level of the dynamics instead of acting at the level of the world, right? So we are given a 2D cellular automaton, and we want to take somehow a continuous limit. So the problem is that each pixel has values between 0 and 1s. So if we consider a small neighborhood, there will be a finite number of neighborhoods, so everything is discrete. But if we, for example, consider bigger and bigger neighborhoods, if the rules don't care about the precise details of the neighborhood, so for example, holistic rules, which looks at the sum of the pixels of the neighborhood, what we get is that we get smoother and smoother dynamics as the neighborhood gets bigger, right? So if I get 1,000 pixels in the neighborhood, and then my dynamics depend kind of smoothly on the number of lit pixels, you can see that we approach some kind of smooth dynamics in this way. So yes, so in this example, so in this case, you have to be careful, right? Because in some way, yeah, my analogy is kind of bad, because as you scale the side of the neighborhood, you're supposed to also scale the size of the world, right? Because, for example, in the game of life, you have a 3x3 kernel, right? The evolution rule are the one we know. So if the neighborhood is a quarter full, you survive. It's a third full, you birth, and otherwise you die. If you get now a 300 by 300 pixels world, okay, you get 100 by 100 neighborhoods in your world, right? And this really sets the scale of the world. So the size of the interaction is the size of the kernel here. If you get a much bigger, why did I finish my, yeah. So in, let's say in larger, wait, is the example later maybe? No. So yeah, so in the game of life you have this. So if you get some larger game of life, for example, okay, let's say you have a, I don't know, a 50 by or 100 by 100 kernel, okay. Then the evolution rules are the same as before. So you count the number of live and dead cells and you evolve. So the problem is that now in a 300 by 300 pixels world, you get only 3 by 3 kernels, okay? So in a sense, by growing the kernels to be 100 by 100, you shrunk your world to be 3 by 3. Because before, if a glider took like 5 cells, okay, the gliders needs like 2 or 3 kernels. Now the gliders takes 300 by 300 cells. So this will be clear. I feel it's not very clear right now, but let me continue a bit. Okay. So if we want to smooth the game of life, so we want to preserve dynamics which are similar to the game of life, but we want to do it more smoothly. So what we do is use a bigger kernel, okay? So remember before we mentioned the kernel, the convolution, etc. So when I say kernel, I mean neighborhood. It's the same thing. So in the game of life, we have the 3 by 3 neighborhood. When we zoom out, we can emulate it by either this neighborhood or this neighborhood, okay? Here there are two interpretations, whether the 3 by 3 of the game of life really means that you interact in a square, or if it's an approximation of a circle in low dimensions. I would tend more towards the circle, but it could be either one. So yeah, let's try to translate the game of life rules with this bigger kernel. Okay, and that's what I was trying to say before. I got a bit mixed up. So because we'll get a bigger kernel, we will also need a bigger game world to get the same amount of zoom. right? So the kernel, the size of the kernel should really set the scale of your world. So the kernel is size 1 centimeters, and then the world is counted in number of kernels. So the example I was trying to give before is that if you have a 25 by 25 kernel, a small glider which needs 2 kernels to exist will be 50 by 50 pixels. Okay. So in Game of Life, the same glider would take 6 by 6 pixels. So when we increase the neighborhood, what we are doing is inside zooming the world in and zooming in the dynamics. Yes. So we can see increasing the size of the kernel as zooming in and resolving the final details of the interaction, right? So this is very qualitative. Okay, it's not precise. And in practice, you will see that this doesn't work one-to-one. So you need to tune the dynamics actually a bit when you do this zooming in. And here I just want to show some examples of what you can get with this processor. So there is this model which is called larger than life. And this model, what it attempts to do is exactly what we mentioned before. So it attempts to take the Game of Life, get a much bigger kernel, and attempt to preserve dynamics which are similar. Okay? And the most well-known rule is bugs, which is the one that is inspired from the Game of Life. And it uses it as 5.5 times 5 neighborhood. And it is holistic, so the rules depends only on the sum of the cells. Or outer holistic, I should say. Right, so if S is the average of lit cells in the neighborhood, the rules are as follows. Okay. Between 0 and 33%, we die. So this is the same as the Game of Life. If you have less than 3 lit pixels, you die. Between 3 and 45%, you birth or survive. So these are the ideal conditions. Between 45 and 68 and 60%, you survive. This is less than ideal, but you survive. And this is the overcrowding. And if you look at the dynamics of this model, we get something which is very similar to the Game of Life. So we have these gliders. And then here, I want you to look at these things here. These things are also very similar to what happens in the Game of Life when you have the things that boil. But overall, it is much, much less diverse. Okay, so this is one thing I noticed from experience. Usually when you go to these smoother models, you get much less diversity, even though here we are essentially attempting to simulate the Game of Life rules. You see the still lives. Okay, we have 2 types of still life, the squares or these circles. Then you have the gliders, but beyond that, you don't have much else. If you start with the same condition in the Game of Life, you will see a lot of blinkers, things, and it goes on from much longer. So that is the question, why is the continuous model or the more continuous model less rich? This is not so clear to me. But at least we managed to do what we want, okay? The dynamics looks much, much smoother. All right. So then you have the extension of this larger than life to multiple neighborhoods. This you can do either in discrete or continuous model, is the same. So this is because when we increase the size of the neighborhood, we also get much more possibilities for the rules that we can do. And usually, as always, one imposes some symmetry constraint, which is usually rotational symmetry, and a max size for the neighborhoods that you consider. So you cannot consider neighborhoods which are too big. Okay, for once, because it's hard to simulate, and twice, because we said that then you need bigger and bigger worlds to actually see some stuff happening. So then you have lots of different kernels that you can choose here. Okay, so these are all rotational symmetric, at least approximately rotationally symmetric. And then you can have more neighborhoods for each cell. Okay, and this is what MNCAs are, multiple neighborhood cellular automata. So they are simply cellular automata, which usually have bigger neighborhoods of this size and different kinds of neighborhoods. And what happens is that what you do is compute the sum of live cells in each of these neighborhoods, and then you get 3 numbers. And then according to the value of these three numbers, you do different things. So this is an example for when you have two neighborhoods. One rule could be if the first neighborhood is more than 33% occupied and the second one is less than 50%, then you birth. Then you have a huge list of things. And this model is, of course, exponentially richer in the number of neighborhoods because you can mix and match what happens for each channel when it's activated or not. But this also means that it becomes much, much harder to guess good rules that gives nice dynamics. Okay. So here you need to either be very experienced or develop some automatic search of interesting things. And so there is one guy, which is kind of the big professional of MNCAs, which is Slackermans. And I highly recommend to go take a look at his YouTube channel. It has like 50 subscribers, but he has, I don't know, 200 videos of things he found. And so here is one example of a multi-neighborhood cellular automaton. You can see it's already much more lifelike because we are much more continuous. So we have these worms. And this is one which is relatively simple. Okay, this one was obtained according to Slackermans with manual tuning. So the rules are like 5 or 6 lines, not too complicated. But again, we see this kind of trend, which I would love to have an answer for, that as you get more continuous, you get less diverse. Here we have one kind of creature, is the worm, and that's it. And this one is another, which was obtained by random mutations. So now I don't know what it means by random mutations. So he fixes the multiple neighborhoods, and then the mutations are on what values make you birth, what value makes you die, survive, etc. But what he doesn't say is how does he select, how does he direct the mutation? Is it like he just does random mutation and then looks if it's interesting, or it has a way to select automatically what looks cool and what not? This I don't know. I should probably send in an email to ask. But you get these kind of more complicated behaviors. And so this is for a model which tends to become continuous in space, right? So here things looks reasonably smooth, but the state in itself, it's always discrete, right? Each pixel is either a 0 or a 1. Of course, when we zoom out, it looks a bit more like smooth, but it's still discrete in the sense of the states. Right, that's what I wanted to say here. And there is no obstruction, okay? In principle, we can also make the state be continuous, but then we must change the rules to become a smooth function, okay? Now we cannot say either birth or die. If the state is continuous, you have to say, okay, you become a bit more alive or a bit more dead. And that's precisely what we'll do in the next course. This is what we will do when we look at Lenya. Okay, Lenya is the actual continuous, both in space and in states, version of the game of life. Okay, and one last thing is another possible extension is to add more channels. Okay, right now we have just one channel, the channel which is either black or white. Okay, now if we say, let's say we have 3 channels, so we have 3 values for each pixel, a red, a green, and a blue value. And okay, now this is not particularly interesting if the channels don't interact. So we need also to add some interaction between the channels. And this is done by considering neighborhoods of this kind. So right now your kernel, not only it asks whether there is a live or dead cell at a location, it asks if there is an alive or dead cell of a specific color. Okay, so this is a kernel. For example, the kernel looks if there are blue pixels close to us, red pixels here, and green pixel here, and then it computes the average number of the red, blue, and green pixels, and it gives you an answer of there were that many green in the region, that many red, and that many blue. And then you get this number, and then you can choose what to do with this number, which is again much, much more complicated. You have always more and more parameters to fix. And yeah, and the additional thing is that now each of the channel may have its own set of kernels. They don't have to have the same kernels. For example, the red channel uses this neighborhood, the blue channel uses this one, the green channel uses this one, and so on and so forth. Okay, you get an immense amount of free parameters. So now I really don't know how you do it manually. So you really need some way to kind of automatize. But the kind of things you get is really impressive to me, the behaviors you can get. So this again from Slackermans. And these are all multi-neighbor cellular automata with relatively big neighborhoods because it's very smooth. And you have the three channels, the red, green, and blue. And you have some cross interaction of the channels. And we see these very complicated solitons appearing, and you have these interactions between solitons. They are quite robust. But again, we still have this problem of, for each set of rule, we have one kind of soliton, or maybe two. Okay. But still, it's very, very impressive what you can achieve with this. And I would be very curious to know how does he look for this stuff in an efficient manner, because the amount of video he has is so big that he must have a trick. So yeah, so these are the multiple neighbor cellular automata. And at the end, yeah, I put just a list of some models, some discrete models, which I did not present. So you have Langton ant. You might remember it from the very first lecture. So this is the one where you have an ant that walks on pixels, and according to the pixel color, it goes left, right, up, or down, and it changes the pixel color, and it gives some nice stuff. Then you have the falling sand models. So these are models where each pixel has a specific property and it interacts with pixels differently. So one example is this one. You might have seen it on the website. They usually look like this. This one is already ready. Let me reset it. Right. So here, for example, you have the water pixel. So the water pixel fall down, and then when it encounters other water pixels, it's kind of flow along them. And you have the sand one, which is like water, but instead of flowing along them, it kind of makes some pyramids. It flows less than water. And then you can do many different pixels. And you can do a kind of some small ecosystem simulation. The most advanced version of a falling sand model from the point of artificial life is this BioMaker cellular automaton. So it's a falling sand game with agents. So you have plants which can reproduce, etc. So take a look at that if you're interested. And also you have this video game that some of you might know, Noita. So it's a video game where all the physics are essentially cellular automata. So you have different properties that can interact, etc. And you have to evolve in this world. Okay. The biology LGCA I mentioned. The lattice-Boltzmann models is the evolution of the LGCA, where instead of considering individual particles, you consider concentrations of particles. It makes it's a bit more flexible because you don't need to scale so much to get something which looks like a fluid. And yeah, I think that's about it for the discrete models. Any questions about this? It was a bit fast, but. All right. So I guess it's 8 here. Let's begin with the reaction diffusion models. So reaction diffusion models that I will present today is the first example, probably also historically, of a continuous model which is related to artificial life. And one important thing that I will kind of underline is the connection it does with discreteness. Okay, we'll see that it is a way for discrete things to appear out of the continuum. Here you have some references if you want to take a look at Turing's original paper. And there is this website, which we'll look at it later. And yeah, for the people who are interested, I will do a 15-minute tutorial on the code base for the cellular automata, if you're interested in that. It won't be live, I'll just put it on the website, so keep an eye out for that if you wanted to implement something with the code base. And last technical thing, probably later this week or next week, I will send you a poll to vote for which day you prefer to do the presentations of the projects. Yeah, so let's get started. Right, so from continuous to discrete. So until now, we looked only at discrete models. Okay, at the end of the previous course, we looked kind of the connection between discrete and continuous. And we saw that it is usually quite costly to kind of simulate the continuous with a discrete model, because you usually need either huge neighborhoods, as we have seen, or millions of particles to actually get something that starts to look continuous. So if for some reason you're more interested at the continuous or at the scale in which things look continuous, it might be more efficient to directly look at the continuous version of the model. Okay, for the example of the LGCA, it might be better to look directly at the Navier-Stokes equations and solve those. Right, so in that case, the choice of whether you want a discrete or continuous model depends on what you want to model and what scale, at what scale do you want to model it. Okay, so an example that I wanted to give is, if you want to model something at the level of the cells, and you want to model the cells as individuals, then probably a discrete model is better suited, right? So the cell will be kind of a discrete entity that can take some actions. And so you modelize this as such, and then you can look at how the cells cooperate, etc. On the other hand, if you want to modelize concentration of chemicals in a solution, for example, at the human scale, so you have a solution, kind of a centimeter of solution, the correct way of doing this is probably not to model the individual water particles, but to actually consider this as a fluid, a continuous fluid, and use a continuous model instead. Okay? So the problem in artificial life is that it is often interesting to be precisely at the scale where it's not clear whether you should model it as discrete or as continuous, right? So you really want to understand how this larger scale emerges from the rule at the lower scale. Okay, so in that case, you might want to see how the continuous part comes from the discrete, or conversely, how the discrete comes from the continuous part. Right. So in life, usually, or at least, we are kind of biased. I would say, or I'm biased by physics. In life, we usually expect discrete entities to emerge. At least we're biased by our everyday observation. So animals are kind of discrete entities. We are discrete entities. Although you have some creatures like slimes, which is not clearly clear how discrete it is as an entity. But yeah, so essentially in life, we want this emergence of discrete entities, even though at the scale of the emergence of these discrete entities, for example, the cells, the underlying medium looks continuous. So the cells, they evolve in water, and at the size of the cell, the water is continuous, right? It's not discrete. So another example is at the scale of a mouse, the cells that make up the mouse, okay? The mouse is emerging from the cells, the combination of the cells. And the cells themselves are discrete. So you have discrete emerging from discrete. But at the level of the mouse, the cells composing it look continuous. Okay, at the scale of the cell, the chemical solution in which it appears looks continuous, I think, at least, for most cells. So, okay, that's what is a very long introduction, just to say that today we'll look at a continuous model, a reaction diffusion system, which displays the emergence of discrete dynamics at larger scales. Right. And let me put this in parentheses. It also admits an analytical treatment, in the linearized regime. So if you're more interested in theory, the reason to consider this rather than another is that it lends itself to some analytical treatment. Right. So before starting for the actual model, some important thoughts, which I think I've repeated many times, but let me say them again. The first part of the course were all about Turing completeness, how it's very related to reproduction, etc. But as we presented it, Turing completeness really requires discrete elements, right? We have the tape, we have discrete elements on the tape, we can go left or right in discrete steps, etc., etc. So naturally, you have the question, what does it mean for a continuous system to be Turing complete? Can you really define what is a discrete state in a continuous system or not? And the other question, which is also very important to recognize what is a discrete entity, is can you define rigorously what is a discrete entity if your medium from which it emerges is continuous? Okay, and a partial answer to this will be the course on the KdV equation. All right, so any questions about this? All right, let's start into the model proper, then we'll do the small break. So reaction diffusion models. So what are they? So before defining the model, I just want to make a small diversion to actually ask the question, what does it mean? What do I mean by continuous model? When I say we have a continuous model, what do I mean? So in a cellular automaton, as we defined, the discrete one, right? We have a discrete set of state, which we'll call S, a discrete space, okay, usually it's a two-dimensional grid, could be higher, which we call X, and discrete time steps, which we call T. Okay, these are just the names for these three things. They're not like rigorous or whatever. So in the case of the cellular automaton, the master equation looks something like this, right? So A describes the state of your world, okay? So A is a function that gives you discrete values for each position, which is also discrete in space. And we compute A at the next time step from a transition function acting on A at the previous time step. And we can consider only the neighborhood of our state here, right? So this equation here in words is state A at time t plus dt and at position xi is determined from the transition function applied to the neighborhood n of xi at the previous time. So for CAs, remember that we never really defined what is this delta t. It's just a discrete time step, so there is no reason really to put a value on it. So usually we have delta t equal 1, right? We have discrete time step 0, 1, 2, 3, etc. Same thing for the neighbors. Sorry, we don't say that a neighbor is at distance delta x. We just say that we have a neighbor at location 0, 0, and then location 0, 1, right? So this means that formally in this definition, delta x is equal to 1, right? Because it's discrete, so any value will do. So let's see what it means to take the continuous limit or to consider the continuous counterpart of this model. So we have several options, right? We have these three things which are discrete, and we can make them continuous. So if we make the state continuous, what does it mean? Well, it simply means that the function a of x can take values in a continuous space, right? From the game of life, we can have 0 or 1. The continuous version is each pixel can have values in 0 all the way to 1. That's quite simple and quite clear. So how do we make the time continuous? Okay, so here it's important to have the delta t which is defined, right? So taking time to be continuous means that somehow you can take this delta t to 0 and still have something that makes sense. Okay, one example would be the following. So if you have the following dynamics, so E at A of t plus delta t is A plus 2 times the time difference between the two. Here it is sensible to take delta t to 0. Okay, why is it sensible? Well, if I rearrange this and divide by delta t, I'll get the derivative of A with respect to t, and so the limit is defined. we are allowed to make t continuous. Same thing for x continuous. It means that delta x can be taken to 0 and get a sensible result. So usually it will just become, something will become a derivative, usually. Right. So now the last thing that I want to mention is that here we say how to take the continuous version of each of these three aspects, but they cannot always be taken to be continuous independently. Okay. What do I mean by that? Well, if we take the time to be continuous, very likely, maybe there are some edge cases where it's not necessary, but you will need to take S to be continuous as well. Okay. And the intuition behind that, same for X, right? Whereas S, I can take to be continuous independently on whether time or X is continuous. So the reason for this is that to take the limit of t and x, we usually introduce derivatives. Okay, as you see here, when we take the limit delta t to 0, is because we are taking a limit of a derivative. And of course, if you want this derivative to exist, you need a to be differentiable, right? So in particular, if a can take only values in 0 and 1, it will not be differentiable, and so you will not be able to take the limit. Same thing for x. So another way to see this intuition is that consider a state, take the continuous t limit when s equal 0 or 1, right? So we keep the s discrete and we try to take the t limit. As delta t goes to 0, the fluctuation of a should become more gradual. Otherwise, you get kind of, if a can be equal either to 0 or to 1, imagine the game of life where you speed up the game of life immensely. Everything starts blinking infinitely fast, and then you don't have a good limit. So if you want gradual changes, because the time step is slower, so everything should slow down, you need continuous variables, and so you need s to be continuous, right? So more generally, although it will not always be true, so when I say that I consider a continuous alive model, what I mean is that both t, x, and s are continuous. So continuous spacetime, continuous states. All right, so with this being said, the equation, the master equation, let's say, for continuous model will be something like this. So usually we'll have a partial derivative on our world state A, and this will be equal to a function f, which is the equivalent of the transition function, or rather it is a functional more than a function. And this f is allowed to act on A at time t and y, where y is in some neighborhood of x. This is the master equation, which is very similar to the one for cellular automata. And let me say one last thing before the break. Right. Yes, so f, as we said, is an operator on A. So it can be a derivative in x. It can be an integration in x. It can be whatever you want, but it has to act at a fixed time t, right? And it cannot take derivatives in time in particular. Yeah, so this notation here, where I write here, so this means that the operator f can only use values of y which are in the neighborhood of x. Okay, so if you want to say it mathematically, I think it would mean f has support in yeah, something like that. But anyway, yeah. No, it's not that. Yeah, it's no, because f is fixed. It does not depend. Yeah. It should not. Yeah. No, you're right. Yeah, what I want to say. Okay, yeah. Let me not say mathematically for now.
You change it outside, it doesn't change that.
Yes.
That's kind of
Yeah. Yeah, okay, but I can just say that F has compact support somehow, and it kind of works. But then here I have to write in okay. Let me not make mathematically precise. I'll do it during the break. But okay. So the last thing I want to say, yeah. So here this F can act on the neighborhood of Y, of X, sorry. And if you have a specific model in which for the neighborhood of X is just X, okay, we'll call this model local. Okay, one example of a local model is the following. We have the partial derivative of A is equal to 2A plus partial derivative of A according to X. As you can see, the left-hand side here, the right-hand side here, depends only at A at location X and its derivatives. So this is a local continuous model. And this one is a non-local one. I should probably write X plus Y, right, like this. This is a non-local model because, as you can see, it uses the values of A around X, not only at X. Right, and the last comment before the break, sorry for the late. Right, so if you remember, if you draw the analogy with cellular automata, which are discrete, if you have a local cellular automaton, you cannot have any transfer of information between two adjacent pixels, right? Because the state of a pixel depends only on the state of the pixel before it, so it cannot communicate around it. Whereas here, even for a local continuous alive model, you can have transfer between neighboring pixels. And the reason for that is that you're allowed to have derivatives. Okay? Even though derivatives is local in principle, it does transfer information from the points around it. Because to compute it, you need to take this limit from around the point at X. And so the reason you have this derivative allows you to have things that move in space, even though the model is local. Yes?
You're just like when you write nx equals x, how can you take derivatives of A in that case?
Right, yeah, good point. So how should I say it? Yeah. Yeah, the better way to say it is that F is really an operator on A. So it can act with kind of these linear operators like derivatives, etc. And then a local operator is the one, yeah, I see your point, yeah. That in principle, if you can only add on X. So this is not a good...
Like what you mean in some sense that if you change A away from X, like a positive distance of X, you don't see it in...
Right, yeah, this is what I mean.
It's by a derivative.
Yeah.
Support.
Yes. No, yeah, that's a good point, yeah. Yeah, I should rewrite this to be a bit more rigorous. But in essence, what I wanted to say is that you can have A or its derivatives evaluated in X, and then you can cook up anything you want with this. And this is still local, yeah. Other questions? All right, if not, let's take a 15-minute break. So let's be back by 22. C'est vrai ça, parce que en physique... Okay, let's restart. Right, so we have this definition of continuous models. So the last thing I wanted to address is the fact that here, you might have noticed, some people have noticed, I don't have much freedom on what I do with the partial derivatives in T. Okay, you might ask, okay, why just one partial derivative? Why not two? Why not three? Why not have a cosinus of the partial derivative in T or whatever? The reason for this is because, the reason most models use only a single derivative in time. And the reason is that the analog of a cellular automaton, the single time derivative is the analog of the cellular automaton. Why? Because the cellular automaton depends only on the previous state to determine what will happen next. So given a cellular automaton, all you have to specify is the initial state of the world, and then you can just let it evolve. For differential equations, the equivalent of this is that for a single partial derivative in times, it means that to fully specify the future of the model, you just need to specify the initial state of the model, and that's enough for the problem to be well posed. Also, more generally, it is easier to get things which do not oscillate with single derivatives in time. Yes?
And more generally, I think any model with any derivatives in higher derivatives can still be written as a single derivative in time.
That's true. Okay, that's yeah, that's maybe a better way to put it. That even if you have more derivatives, okay, you can do this trick where you kind of define new variables which are derivatives in time, and then you can rephrase it as a single derivative in time. That's true. Yeah, I cannot really say anything about that. It's true. But usually we'll stick with real ones, which are not like kind of a disguised second derivative in time. But in principle, that's true. Yes. Yeah, so in general, we could also have, there also was a question about this, a model which is non-local in time, meaning that the state of the model at the next time step depends not only at what happened at the very previous time, but also at a distant location in time. Okay, why not? Okay, yes, question? Yeah, so this is the usual trick that when you have, essentially when you have a set of differential equations, partial differential equations, if you have a second derivative in time, you can just define a new field, okay, to get rid of the extra derivatives in time, okay. You can define a new field, sorry. So the new field would be something like A prime is equal to, but it really is just a trick. I mean, it's just a rephrasing. Okay, so what you do is that you add one field to your model, which is A prime, and you add one equation for this field, which is A prime is equal to partial A of partial t, right? And then everywhere you have a second derivative of A, you can replace it by derivative of A prime. So what you're left with is with one extra equation, but only first derivative in time. So for example, with this, let me write it, partial square A, partial t square becomes frac partial A over partial t, and this is A prime, right? But it's, I mean, it's just a rephrasing. So in principle, you can phrase everything with a single derivative in time. In practice, you're cheating. You're just hiding it into a definition of a new chemical. Okay, reaction diffusion models, finally. So reaction diffusion models, they are a class of continuous and local models with a single time derivative, as we described above. All right. So generally, what is the reaction diffusion model supposed to describe? Okay, what is it good for? So it is supposed to be a model of the interaction of K chemicals, okay, which we'll denote by AI, T, and X. And again, yeah, so you have K chemicals, A1 through AK. And you can do these equations in any kind of spatial dimensions, but will restrict us to two-dimensional space, right? So X and Y. So this X will be both X and Y. And the master equation is the following equation. So you have two terms, a diffusion term and a reaction term, hence the name. So you see immediately that, let me make it more clear. in Tx, right? So you see immediately that this is a local model because on the right-hand side we depend only on x, not on the neighborhood. And this Laplacian, this delta A is just the Laplacian, right? So the di's, these di are constants, the diffusion coefficients, and the fi is just any arbitrary function of the chemicals. Okay, be careful not to mix up this fi with this f here. This fi is much less general. Right? This fi cannot have derivatives in x. It really depends only on the value of the chemicals at the point x. Okay, no derivatives. All right, so let's break it down in two pieces for the people who haven't seen this. Maybe people from physics certainly have seen this, people from other fields not sure. So what does the diffusion term do? Okay, and from the names, the diffusion terms come from fluid mechanics, and if you look at the Navier-Stokes equation, it describes the so-called diffusion process, which is how do chemicals kind of spread in water when there is no current, right? We are not putting any kind of current. The chemical just spreads out when it has a high concentration. And microscopically, this is due to the particles which are kind of randomly moving. Overall, this makes a spread. So this is what the diffusion process looks like. So here I have two chemicals. You start with a high concentration in the middle. And as you can see, the diffusion tends to kind of spread out this concentration, as you would see in water. And here I have the two chemicals. The chemical on the left has a higher diffusion coefficient from the chemical on the right. Okay. All it means is that it will diffuse faster. Okay, so this diffusion coefficient just tells us how fast the chemical is spread out. All right, very simple. And as you can see here, on the right-hand side, the diffusion part is the only one that contains space derivatives. Okay? And as we said, the space derivatives are the one which are responsible for the interaction among neighbors. So in a sense, the diffusion term is the only one that will make things move, okay? Because it's the only one containing derivatives. So in particular, we will usually get things which move not too fast because the diffusion process is something that is relatively slow in movement. All right. Then we have the interaction part, which is somehow the full meat of this system because it's a nonlinear part. And that is what will allow us to have some kind of strange emerging dynamics. And in principle, this function here can be completely arbitrary. Okay? We have no constraints on this function. But in practice, it's nice to put some extra constraints that ensure that we don't have exploding solutions. Because, okay, if we have a model in which you get something which goes to infinity, then it will be kind of hard to visualize, especially. So, okay, although in practice, the examples we will see do not tend to respect those. Okay, so the condition I will tell you are kind of very strong conditions. They're not necessary, but they're certainly sufficient to get something which is stable. So for this, we'll say that concentration of the chemicals can go from 0 to 1, just arbitrarily. Okay. 0, you have no chemical. 1, you have the maximum concentration for this chemical. So we know that the diffusion part, we don't have to worry about it, because the diffusion part, all this does is kind of homogenize the values of the chemicals. So if everything is between 0 and 1, the diffusion process is not going to hurt us in some sense. So the only problem is with the reaction term. Okay, what are the conditions of the reaction term such that we don't get stuff which go crazy? So the first thing is we don't want things to go negative. So when a chemical is equal to 0, we need the reaction term to push it up. Okay, so we need Fi to be bigger than 0. And vice versa, when the chemical is at the maximum concentration, we need the reaction term to push it down. And this should hold for any value of the chemicals. And that's the only constraint we need. And if we do that, we'll have things which are well behaved, very nice, very easy to visualize. But in practice, it's not like that, unfortunately. But, yeah, so here I just have a project idea, which is something that I wanted to do for this course, but actually it's harder than I expected. So this would be to explore the reaction diffusion model for random reaction diffusion. Random is a big word, but from random functions. So we have several problems if you try to do this. Is how do you get a random function overall? This is a difficult question. How do you enforce these constraints such that you get nice thing? And lastly, do you get, if you choose such a random function, do you usually get something which is actually nice, or you do get some trivial dynamics, so just nothing happens or whatever? I think it's an interesting question. I don't think it has been studied very much. So about the simulation, I think I will skip this for now, and then we can come back to it if need be. This is some technicalities on the simulation. But yeah, let's rather look finally at some specific reaction diffusion models. Okay. So as we said, the space. There was a question that I missed from Esan, was, is physics local in this sense? And the answer is yes. Okay, so if you go at the fundamental level of physics, you will have the things that describe physics is completely local in the sense that I mentioned above, so that physics depend only on fields at the point and their derivatives. So that's true, yes. If you go at larger models like biology, you might need something which is non-local if you want a good modelization. But in the case of physics, it's true. Okay, let's move on. Right, so I said, so the space of reaction diffusion model is just too big, right? Because you can choose literally a random function of many variables. So what people usually do is that they do not study reaction diffusion as a whole, but they study a subset of specific function which take a specific shape. So here we take a look at the most famous examples. So the first one is the Gray-Scott model. I think this is the one people visualize when people talk about reaction diffusion. And the way you build the equation from a chemical reaction is interesting. So let's go through the steps. So the Gray-Scott model, what it is supposed to modelize, I don't know exactly where this arises in nature, but it does, is that we have two chemicals, U and V, and they have some chemical reaction, which is the following. So U plus 2V gives us 3V, all right? So this chemical reaction consumes U and creates V. So if we start to model only this chemical reaction, we'll get something where all the U will be consumed. You'll get a full range of full state of only V, and so it won't be very interesting. So to get something which is sustained, what we'll do is we add a feed mechanism to U. So we'll constantly add some U chemical, and we'll constantly remove some V chemical such that we can get something which remains interesting. So how do we go from this to the actual reaction diffusion equation? It's very easy. So we write the reaction diffusion acts on the concentration, right? It's a continuous model, so it's no longer particles. We act on the concentrations of U and V, which we write U and V lowercase. So for this reaction to happen, if we look at the particle level, what needs to happen is that you need somehow to have a collision of one U with two V's, right? So how do you interpret this in terms of concentration? We interpreted this as being that the probability of this reaction taking place is proportional to uv squared. Okay, why uv squared? Because we need two v particles. Okay, the probability of get two v particles is proportional to the density squared, and then one u particle. This is just proportional to the density. So the total probability is uv squared. Okay. So the first step in our equation is adding the effect of this reaction, and we get this equation here, right? The change in u will be negative. We'll subtract u whenever this reaction happens, and this reaction happens with probability uv squared. For v, it's the opposite. We get from 2v to 3v, so we add 1 unit of v each time this reaction happens. So now for the feed and kill rate, so we can do many things. So we could add a constant feed rate to u and a constant kill rate to v. So we always remove v and add u. But this won't work with our stability conditions, right? So if we take v equals 0, we see that we are still reducing v, so we'll get a v that goes to minus infinity, which is no good. So we amend this, and we say that we feed u proportionately to how much u we need to put, and the same for v, right? So if the u is very low, we will feed at the full rate. If the u is equal to 1, there is no need to feed, so we stop the feeding. Same for v, we'll remove it only when there is a lot of v, otherwise it's not necessary. And now you can check that this indeed satisfies the stability conditions that we mentioned before. So if you take u equal 1, you will get a negative contribution. If you take v equals 0, you don't get a negative contribution, and so on and so forth. At least I think. Yes. No, okay. When v equal 1, you may get a problem, indeed. If k is yeah. So you would need k bigger than 1 in this case, which is not actually the case in, in the simulation, so almost. Okay, that's what I mentioned, yeah, that it doesn't always satisfy the stability condition. And there is a slight modification in the end. This is not a real modification, but instead of here removing v at the kill rate, we'll remove v at the kill plus feed rate. This, they say, when they define it, is to make sure that we remove v faster than we create u. But intuitively, it's not clear to me why that should be true. I think people just tried it and noticed that you needed a kill rate which is bigger than the feed rate, and that's why they choose this. But all right. Okay, this is the reaction part. So all we need to do is just to add the diffusion terms, and we get our Gray-Scott model reaction diffusion equations. So now this is much nicer than the initial reaction diffusion, because all we need to change is these 4 parameters to explore the space of what can happen. So let's see how it looks in practice. So I did implement this in my code base. Let me see. But it does look nicer. Since this one is so famous, it has been implemented in many places. So after that, I will show you something which is even more beautiful. But let's take a look to see if it works. All right, so we start. So white and blue are the 2 colors of the 2 chemicals. So we start with a full state where everything is covered in U, and with a small dot of V in the middle. So if we let it evolve, it's a bit slow. Let me. That's strange. Okay, let me try it again. Okay, right, that's better. Okay, we have this thing that grows, and then at some point it starts to get some structure, right? And we have this kind of generation of this beautiful pattern, which respects. So we have already a symmetry breaking here because we started with a perfect circle, and we get this thing which is only 90 degrees invariant. And this is because, of course, the circle that we do is actually not perfect. It has some slight imperfection because I have to discretize the model. And then you can play with it. And here, in principle, I can also, I broke the model. So let's go to the website, which is a bit easier to work with. Yes. So this is an implementation which is made online, and this is the exact same parameters that we had before. And here you have kind of a phase space according to the feed and kill rate. You can get very different behaviors. So yes, you can get behaviors like that where you have moving things. You can also get reproducing particles. Yes, this is one example of particles which reproduce. And then you can get some worms as well. Yes. And this is all depending, all we're varying here is the feed and kill rate, and that's it. And this website, yeah, if you can play with it, it's very nice. Here you can also add things which we did not, which is flow to the equation. So remember, in the equation, we only have the diffusion term, but you can very well add a term which adds a speed to your liquid, and that's what they do here. So swirl, bubbles, etc. This is all flow equation, which allows you to see what happens when you make the system flow. Okay, so that's the Gray Scott model. So this is the kind of thing. So if you have to remember one thing, this is the kind of patterns that you see. This is what you associate with reaction diffusion model. That isn't to say that you cannot get some things which looks differently if you choose the function correctly, but that's usually what it looks like in the reaction diffusion models. All right. So this is this set of equation. And maybe, yeah, okay, now let me show also the other examples because we have a few questions here. So another example of a reaction diffusion model, which is kind of famous, not so much though, is this rock, paper, scissors reaction. So you have three chemicals this time, and they have, so A wins against B to produce more A, C wins against A, and so on and so forth. So you have this kind of trifecta of chemicals. And so the first question here that I want to ask you, if you are on the Slido, is what is the reaction that describes this set of chemicals? So the reaction for chemical B, the question is for chemical B. Only the reaction part. Okay. One more minute, and then we'll take a look at the results. Oops. Okay, we have a few answers that came in. So people have correctly understood the way to get the equations. So the answer is dB over dt equal BC minus A. This one, so people got it correctly. And it's the same logic as before, right? So you look at the equations, what's on the left tells you what is the term to add. So for example, this BC chemical reaction will be proportional to BC, right? This BC term. And it creates one B element. So it will appear positively for B. And then this reaction here is again AB, and it appears negatively because it consumes one B. So this is the equation that we have. And so the full set of the system is the following here. And so now we have a second question, which is whether this set of equation respects the stability conditions that we set before. All right. So actually, in this case, I disagree with the majority. So people said yes, and I would actually say no. The reason is because the stability condition that I mentioned is really a very strong requirement, which is usually not satisfied, as we've seen. So you really need to look at the worst case. So in the case, for example, where A is equal to 1, the reaction term for A will be B minus C, bigger than 0. So. And this reaction term may, of course, be bigger than 0, right? So you may have A going upwards of 1, even if all your chemicals are between 0 and 1, right? So if somebody disagrees, let me know, because yes?
So if you consider A plus B plus C, and then maybe dA equals dB equals dC, then you have some sort of...
Right.
Then this will not stay
dA, so A plus B plus C.
will satisfy like...
Yeah, you cancel everything, right? So,
yeah, there's no...
So it's constant. Yeah, okay. But this, yeah, so this is a finer constraint than the one I put before, right? So that's correct, what you're saying. So in practice, because of the rock, paper, scissors dynamics, the system is stable, okay, for the reason you mentioned, that the sum of the concentration is constant, right?
What constant?
But didn't say, so if you sum the three...
It's just that it will satisfy like the heat equation, right?
Yeah, but the heat equation cannot make you go up. I mean, if all the concentration are between 0 and 1, the heat equation cannot make things work. It's not constant. Yeah, sorry. Right. Exactly. So, yeah, kind of trick question. So the answer is no, because my conditions are too strong, right? So my condition is really in the worst case scenario. If I just look at A, if A is equal to 1, B minus C can be positive, so it will violate this thing. But in practice, and that's good, yeah, I didn't think of taking the sum. I will add this as a comment later. Yeah, in practice, it is stable because the sum of the chemicals is kind of not constant, but the average sum of the chemicals is constant. So the problem with this is because I had many problems trying to implement this, is because I have interactivity, right? So I can add, by clicking on the screen, I can add some chemicals. And if you don't have these strong stability conditions, of course, in this case, when I start adding some chemicals, things go haywire because because I can artificially add some B. So maybe these stability conditions that I put are too strong, but they're good for things that you want to interact with. So this is what it's supposed to look like. I haven't gotten it to work, but you get these nice spirals. So the speed and size of these spirals depend on the difference in diffusion speeds of the different chemicals. This will make spirals greater or smaller depending on how the diffusion coefficients are. And yeah, you also have some actual chemical reactions which do something very similar to this, like this one, which has the same name as the model, actually, Belousov-Zhabotinsky reaction. Yeah, so yeah, let me do a last example, which is this Brusselator model. As you've seen, all the models are kind of very similar, right? They start from these chemical reactions, then they write the equation, and you get some sort of spirals. So the Brusselator model is this set of chemical equations, which gives rise to this set of reaction diffusion models. So this is one case where in your dynamics, you don't consider all the chemicals that appear in the equations. This is because for some equation, you suppose that some chemicals are in infinite supply. Okay, so here you suppose that A and B are just some chemicals that are so plentiful that they will never be depleted. And so they appear as constants in our equations. But the way to go from this to this is, again, the same reasoning. And right. And here, yeah, maybe I should have talked about the theory a bit before. But this set of equation, it has some fixed points, okay, at x equal a and y equal b over a. So to find this is very easy. Just plug it in and check that it is compatible with the vanishing of the derivatives. And so the thing is that it becomes unstable for when b is bigger than 1 plus a squared, and that's when you get some nice dynamics. Otherwise, everything is constant. And let me show you what it looks like. So this one I also implemented here, and it gave some nice visuals. So again, I always say this, but if somebody is epileptic, you should leave now, especially on YouTube. Okay, let's start it. So you have two chemicals, and again, they're kind of in one versus another. So when one is there, it inhibits the other, and vice versa. So this is already something very interesting. So you see, I started with a completely homogeneous state, just with boundary condition with zeros at the boundaries. And you can see that there is a complete breaking of the rotational, even the 90-degree rotational invariance. And this is due probably to the floating point imprecision of the computer. So it seeds with a small imprecision. And the fact that the model is completely unstable, it amplifies this imprecision. So it starts like this. And if I kind of add some drawings, yeah, and we let it evolve, right? So here I just seeded it with more chemicals. We start to have these spirals that start emerging and they start growing. And at some point, it overtakes the full screen. You can change color. Yeah, this looks nicer. Yeah, so you have these spirals, they start growing. It looks very nice. It's not very lifelike. And also very similar to these chemical reactions. I haven't gotten it to do much else aside from that. It's nice to play with it and like kind of disrupt the spirals. And then we can modify slightly. I think it works, yeah. So here I am reducing some of the diffusion coefficients, and this affects the speed of the spirals. Yeah, so here the spiral becomes more spirally, if I can say so. So if I increase, yeah. Right, so here I decrease the speed by changing the diffusion coefficients. Okay, and that's the sort of thing you find with the reaction diffusion models. And the last thing that I wanted to talk about, but Okay, this one we can skip. I didn't have much time. So the main question, which maybe I should have put at the beginning, is why did Turing study these reaction diffusion models? Okay. So the title of the paper, of Turing's paper, is the chemical basis of morphogenesis. And so what Turing was interested, the subject that was of interest to Turing was morphogenesis. So what is morphogenesis? Is what happens when you get an embryo, which is essentially a spherical bunch of cells that start to specialize and get some features like hands, eyes, organs, etc. So it's the moment where you go from like a sphere to something which has some specific shape. Okay. And the question at the time, which was strange, is that people mostly believe that the laws of chemistry come from the laws of physics, and these laws are completely spherically symmetric. So it was hard for people to imagine how do you break this symmetry, right? How can you start from a spherical bunch of cells and get a horse if everything is spherically symmetric? Yeah. And so Turing tried to answer this, and the answer to this puzzle is that you have some systems where the homogeneous initial state, just like in the one we just showed, is unstable, right? And so if the homogeneous state is unstable, it means that very tiny deviation from this homogeneous state may get completely amplified and destroy this symmetry. And then what you have to explain is say, okay, yeah, you can destroy the spherical symmetry, but how can you make it so that you always get a horse and the leg is at this location and not at this other location and so on? And so the way that somehow Turing answers this question is that he cooked up these reaction diffusion models and showed that usually you have a few stable equilibria. So when you start with this unstable homogeneous state, then break it, then you will tend to search the space. Okay, this is the part where you don't really know what happens, but end up in a stable equilibrium, which is the one which has the right shape. So you get morphogenesis. Right. So all Turing wanted is a system where you have kind of the possibility of this unstable, homogeneous, or symmetric solution, which can be spontaneously broken by tiny perturbation. Okay, and then you need another set of stable, but not homogeneous solution in which the system settles. And so Turing considered the reaction diffusion models mainly because they were a good modelization for chemical reactions, which is probably what is the main driver of, at the level of the cells at least, is the main force, right? It's chemical reactions. And yeah, so Turing studied this to explain morphogenesis. And just give me like 3 minutes. So how did Turing study this? I may get a bit into more depth next time, but essentially, the reaction diffusion equations, they are non-linearly coupled partial differential equations. Okay, so this is the hardest thing you can get in terms of studying and understanding what's happened. So aside from simulating it like we did today, so how did Turing manage to realize that this is an interesting system? How did he study it theoretically? And the answer is quite simple. Okay, the only thing that you can do is just to consider the equilibrium points, which are easy to find because it's just algebraic equation, and try to make a linearization around these equilibrium points. Okay. Then once you do the linearization around the equilibrium points, you can tell if your point is stable or unstable. And then you essentially get a list of points whether they are stable or unstable. What is the kind of instability you get? And you can get kind of a broad picture of what happens. And he also did some very small simulations, but not much. So yeah, so in the end, at the end of the day, I didn't really say what I wanted to say, which is when we look at this at these reaction diffusion models, we see that we start with a continuous model, but we get the emergence of these discrete elements, right? So we get these kind of little balls, which are clearly discrete portions or discrete creatures that emerge. And so in some way, the reaction diffusion systems give you a concrete example of how to go from continuous to discrete, okay? And then now if you ask me about Turing completeness in this continuous model, I could reasonably say, okay, maybe if you get a model where you get this kind of gliders and you get this non-trivial interaction between gliders, you can generate a Turing machine because now you have discrete elements and you can really do the usual Turing machine construction. So this is just a very interesting, let's say, property of this reaction diffusion model. They are an example where you get the discrete from the continuous. And I think I will stop here because I'm already late. So see you next week.